Any substance that has mass and occupies space is called matter. It is made up of small particles called atoms that cannot be further divided. This idea was first proposed by the Greek philosopher Democritus back in 460 BC. However, due to the lack of scientific evidence, Democritus's ideas were considered mere speculations and ignored for 2000 years until John Dalton proposed the atomic theory of matter in 1808. Dalton proposed that atom is the ultimate particle of matter. This theory is called Dalton's atomic theory. It postulates that all matter is composed of atoms that cannot be made or destroyed. All atoms of the same element are identical. Different elements have different types of atoms. Chemical reactions occur when atoms are rearranged. Compounds are formed from atoms of the constituent elements. Dalton's atomic theory was able to explain the laws of conservation of mass, multiple proportion, and constant composition. However, it could not explain the results of many experiments conducted by the scientists in the later part of the 19th century and 20th century. For example, it could not explain the electric nature of matter as explained by Michael Faraday through his experiment in 1830. Michael Faraday found that when electricity is passed through an electrolyte, which is a solution that conducts electricity, chemical reactions resulting in the deposition of matter at the electrodes take place. This experiment proved that electricity consists of charged particles, which in turn indicated the electric nature of matter. The structure of an atom, however, was demystified only when William Crookes conducted experiments to study electrical discharge through gases in 1879. The apparatus used for his experiments consisted of a glass discharge tube, now called cathode ray tubes or Crookes tubes, and a high voltage source of 10,000 volts. The discharge tube was sealed at both the ends and was fitted with a thin piece of metal called electrodes at each end. It had a side tube fitted with a stopcock that connected with a vacuum pump to control the pressure of the gas or air contained inside the tube. Crookes observed that at a low pressure of 0.01 atmospheres, when high voltage of 10,000 volts is applied across the electrodes of the discharge tube, current starts flowing inside the tube. To further study the behavior of this current, he punctured the anode inside the cathode ray tube and coated the glass tube behind the anode with a fluorescent material, such as zinc sulfide, and then repeated the experiment. This time, he noticed a bright spot on the coating behind the anode, which confirmed two things. One, the current consisted of invisible ray of particles, some of which could pass through the perforated anode. 2. These rays were emitted out of cathode and moved towards the anode. These rays were named cathode rays. Some other facts about the cathode rays were discovered in 1897 by J.J. Thomson and other scientists through a series of experiments. In one of his experiments, Thomson observed that if a pinwheel is placed in the path of the cathode rays, the ray caused the pinwheel to rotate. This implied that cathode rays are made of material particles that produced a mechanical effect. He then observed that if a metal foil is placed in the path of cathode rays, it becomes hot. This implied that cathode ray produced a heating effect. Thomson also observed that if a solid object is placed in the path of cathode rays, it produced a sharp shadow of the object. Therefore, he concluded that cathode rays travel in a straight line. However, when he applied an electric field to the setup, the cathode rays deflected towards the positive plate of the electric field. He observed the same result on applying a magnetic field. Therefore, he concluded that the cathode rays consisted of negatively charged particles, which he named electrons. Through his experiments, Thomson also concluded that the properties of cathode rays do not depend upon the material of electrodes and the nature of the gas present in the cathode ray tube. This led him to the conclusion that electrons are the basic constituents of all atoms. Thomson then tried to calculate the charge to mass ratio of electrons by applying electrical and magnetic field perpendicular to each other, as well as to the path of electrons flowing in a cathode ray tube. He observed that the amount of deviation of the electrons from their path depends on three main factors. 1. The magnitude of the negative charge on the particle. The more the negative charge, the greater the deflection. 2. The mass of the particle. The lighter the particle, the greater the deflection. 3. The strength of the electrical or magnetic field. The stronger the field, the higher the deflection. When only electric field is applied, the electrons deviate from their path and hit the cathode ray tube at point A. Similarly, when only magnetic field is applied, electrons strike the cathode ray tube at point C. By controlling the deviation of electrons by varying the strength of electric and magnetic fields and accurately measuring on the amount of resultant deflections, he calculated the charge to mass ratio of an electron, which equals 1.758820 into 10 raised to the power 11 coulombs per kg. The charge and mass of the electron, however, remained unknown until another scientist, Robert Millikan, devised a method to calculate them in 1909. In order to calculate the charge of an electron, Millikan conducted the famous oil drop experiment by using the apparatus shown here. It consisted of a transparent electrical condenser with one metal plate at the top and the bottom of the chamber. Plates connected to a battery such that the upper plate is positively charged and the lower plate is negatively charged. An atomizer to spray oil into the condenser through a hole in the upper metal plate. A telescope to view the movement of oil droplets. And a source of X-ray to ionize the air inside the electrical condenser. Using the atomizer, Millikan sprayed oil droplets into the electrical condenser. As the droplets fell through the upper plate hole, he measured the rate of fall and used it to calculate their mass. He then ionized the air inside the condenser by passing a beam of X-rays through it. The X-rays displaced electrons from air molecules, which negatively charged the oil droplets. On applying voltage to the upper positive plate, the charged oil droplets got attracted towards it against all gravitational and electrostatic forces. Millikan then varied the voltage to strike a balance between the acting forces and to make the oil drop stationary. He then calculated the change on the droplet from the mass of an oil droplet and the charge on the plate. He found that the magnitude of electrical charge, Q, on the droplets is always an integral multiple of the electrical charge E. That is, Q is equal to NE. Knowing the values of Q and N, Millikan calculated the charge on an electron to be 1.6 into 10 raised to the power minus 19 coulombs. The mass of the electron, or ME, was then determined by combining the results of Millikan oil drop experiment and Thomson's value of E by M ratio, and was found to be 9.1094 into 10 raised to the power minus 31 kgs. Just like the discovery of cathode rays led to the discovery of the negative particles called electrons, the discovery of anode rays led to the discovery of the positive particles called protons. Anode rays, also called canal rays, were discovered by E. Goldstein in 1886, when he repeated the cathode ray experiment conducted by Crookes with a perforated cathode instead of a perforated anode. He observed that discharge tubes containing a perforated cathode also emit a glow at the cathode end. Goldstein concluded that in addition to the already known cathode rays, there is another ray that travels in the opposite direction. Since these rays passed through the holes or channels in the cathode, he called them canal rays. They consisted of positive ions, whose charge and mass values depended on the gas inside the discharge tube. Hydrogen gas produced the smallest and the lightest positive ions, with a magnitude of charge same as that of an electron, but with a positive charge, that is, plus 1.6 into 10 raised to the power minus 19 coulombs, and a mass that was found to be similar to that of a hydrogen atom, that is 1.67 into 10 raised to the power minus 24 grams. The mass of the positive particles originating from the other gases in the discharge tube was found to be whole number multiples of the mass of those originating from hydrogen gas. Therefore, the positive particles from hydrogen gas carrying one positive charge and mass equivalent to a hydrogen atom were taken as the fundamental particles of any atom and were named as protons. By 1913, after performing a considerable amount of research on the charge and mass of negative and positive subatomic particles, scientists tried calculating the atomic mass. It was determined that the atomic number of an element is equal to the number of protons present in its nucleus. It was thought that since each proton has one unit mass on the atomic scale, the mass of an atom must be the number of protons present in the nucleus, as electrons have negligible mass. However, it was discovered that the mass of all protons in an atom put together is much less than the actual mass of an atom. It was thus concluded that the excess mass was due to some other particles present in an atom that had considerable mass but no charge. Later in 1932, James Chadwick proved the presence of these heavy, neutral particles through a series of scattering experiments. In one of his experiments, on bombarding a beryllium plate with alpha particles, Chadwick observed the emission of a neutral particle whose mass was equivalent to that of a proton. He named this particle as neutron. After all the subatomic particles were discovered, it was concluded that an atom is made up of protons or positively charged particles, electrons or negatively charged particles, and neutrons that are neutral particles. The table here summarizes the properties of these fundamental particles.
I wonder, what's the maximum I can score in this game?
You can't score more than the total of the ball points, as the number of balls in this game is fixed. Similarly, based on the study made by different scientists on an atom, concluded that any atom is made of fixed number of charged particles called protons and electrons. This lesson is about the internal structure of an atom. At the end of this lesson, you will be able to define atomic number, define subshells, determine the electronic configuration of an element given its atomic number, determine the valency of an element given its electronic configuration, explain the concept of a neutron based on Chadwick's work, define atomic mass, define isotopes and isobars, and list the applications for isotopes. Scientists propose that an atom is made of two kinds of particles. The positively charged particles are protons, and the negatively charged particles are electrons. Every atom of an element has a fixed number of protons in its nucleus. This fixed number of protons is referred to as an atomic number. This number is constant for an element. It is represented by an alphabet Z. Moreover, the number of electrons in an atom of an element is also equal to the atomic number of the element. For example, if the atomic number of an element is 12, then its atom contains 12 protons and 12 electrons. In an atom, electrons are not randomly placed around the nucleus, but they are placed in fixed energy levels called shells, as per Bohr's atomic model. These shells are named K, L, M, N. The arrangement of electrons in these shells is known as electronic configuration. For example, carbon has 6 electrons. Its electronic configuration is 2, 4. 2 electrons are placed in K shell and 4 electrons in L shell. In order to write down the electronic configuration of an element, one should have knowledge about the number of electrons in one atom of the element and the maximum number of electrons that can be accommodated in different shells of the atom. The maximum number of electrons that can be accommodated in any energy level of the atom is given by a formula 2n to the power of 2, where n is the number of that energy level. For example, the number of electrons present in the first energy level, n equals 1. According to the formula, 2 multiplied by 1 to the power of 2 equals 2. So, the maximum number of electrons present in the first energy level is 2. According to Bohr's model of an atom, the first energy level K can have 2 electrons. The maximum number of electrons which can be accommodated in shell L is 2 multiplied by 2 to the power of 2 equal to 8. Similarly, for M and N shells, the maximum number of electrons that can be accommodated are 2 multiplied by 3 to the power of 2 equals 18 and 2 multiplied by 4 to the power of 2 equals to 32 respectively. During the arrangement of electrons in the shells, the outermost shell of an atom cannot accommodate more than 8 electrons even if it has the capacity to accommodate more electrons. Generally, the outermost shell of an atom can have a maximum of 8 electrons only, even though it has the capacity to accommodate 18 electrons. This is due to the fact that having 8 electrons in the outermost shell makes an atom stable. There is an exception. If the outermost shell is the first shell or K shell, the shell can hold only 2 electrons. For example, helium has only 1 shell in its atom. Electrons in an atom do not occupy a new shell unless all the inner shells are completely filled. The filling of electrons in an atom is a stepwise approach. First, the electrons are filled in K shell, then in L shell, M shell, N shell, and so on. There are few exceptions to this rule, which are applicable to elements with an atomic number more than 18. After a series of experiments and a detailed study by scientists like Louis de Broglie, Schrödinger, Sommerfeld, etc., it was proved that shells have energy levels within them and are subshells. These subshells are S P, D, and F. Electrons are distributed in these subshells. Every subshell can accommodate a fixed number of electrons. The S subshell can hold a maximum of 2 electrons, a maximum of 6 electrons in the P subshell, 10 electrons in D, and 14 electrons in F. Electrons are distributed in their respective shells and subshells. The first energy level, K, can have one subshell which can accommodate 2 electrons. The next shell is the L shell, which contains S and P subshells, where the S subshell accommodates 2 and P shell 6 electrons. M is the third shell and have S, P, and D subshells, which accommodate 2, 6, and 10 electrons respectively. Next is the N shell with S, P, D, and F subshells accommodating 2, 6, 10, and 14 electrons respectively. Let's observe the distribution of electrons in the given 20 elements. Electrons in an atom are arranged in definite shells. The electrons which are present in the outermost shell of an atom are referred as valence electrons. From the octet rule, an outermost shell of an atom can accommodate 8 electrons. It was observed and concluded that an atom with completely filled subshells are stable and do not react easily. In other words, it means that the combining capacities are 0 or nil. The outermost shell of inert gas elements whose subshells are completely filled are stable. For example, helium and neon, where helium has 2 electrons in its outermost shell and all other inert gas elements have 8 electrons. The combining capacity of the atom to form molecules either with the same or different elements is defined as valency. For example, elements like hydrogen, lithium, and sodium atoms contain 1 electron in the outermost shell. Therefore, they can lose 1 electron. So their valency is 1. If atom contains less than 4 electrons in its outermost shell, the valency of an atom is equal to the number of electrons present in the valence shell. For example, aluminium has 3 electrons in its outermost shell, so the valency of aluminium is 3. On the other hand, if the outer shell has more than 4 electrons, the valency is 8 minus the number of electrons in the outer shell. For example, chlorine atom has 7 electrons in the outermost shell. Here, in this case, it is easier for chlorine to gain 1 electron instead of losing 7 electrons. Hence, its valency is determined by subtracting 7 electrons from the octet, which gives the valency of 1 for chlorine. Let's examine the element helium. It was found that helium has 2 protons and 2 electrons. However, its mass was found to be 4 times that of hydrogen. Similarly, the weights of some other elements were also found to be double or more than double the weight. For example, the number of protons in chlorine is 17, but its mass was found to be 35. Similarly, number of protons in mercury is 80, but its mass was found to be 200. This problem was solved when James Chadwick discovered another particle, neutron. Neutron is a neutral particle with a mass equal to that of a proton and is present in the nucleus along with the proton. An interesting aspect came into picture after the discovery of a neutron by Chadwick. Till then, only the atomic number of an element was in existence, which referred to the number of protons present in the nucleus of an atom. The total mass of the protons and neutrons inside the nucleus was regarded as the atomic mass of an element. Therefore, atomic mass can be defined as the total number of protons and neutrons present in one atom of an element. For example, one atom of sodium element contains 11 protons and 12 neutrons. So, the atomic mass number of sodium is 11 plus 12 equals 23. The mass number is denoted by an alphabet A. Now, let's try to derive a relationship between mass number and atomic number. Mass number equals the number of protons plus number of neutrons. Since the number of protons in an atom is equal to the atomic number of the element, the above relation can be rewritten as mass number equals atomic number plus the number of neutrons. The atomic number and mass number can be indicated on the symbol of an element. The atomic number is written as subscript on the lower left side of the symbol, whereas the mass number has a superscript on the upper left side of the symbol. Normally a carbon atom has 6 protons and 6 neutrons, but some unstable carbon atoms were found. These carbon atoms had 6 electrons, but the nucleus was similar to that of a nitrogen atom and it had a mass of 14. Soddy discovered that certain elements had a heavier mass. Their atomic number and chemical behavior was same, but their mass was slightly higher. The higher mass is due to the presence of extra neutrons. Soddy called the elements with same atomic number and different mass number as isotopes, Greek meaning same place. Thus, isotopes are atoms of the same element with the same atomic number but a different atomic mass. The valency of isotopes is the same. Isotopes of the same element differ in their physical properties. For example, 12C6 and 14C6 are isotopes of carbon. 1H1 protium, 2H1 deuterium, 3H1 tritium are isotopes of hydrogen. 35Cl17 and 37Cl17 are isotopes of chlorine. The chemical properties of all the isotopes of an element are the same. This is due to the presence of same number of electrons. Rarely some isotopes have special properties which were found to be useful in various fields. For example, an isotope of uranium is used as fuel in a nuclear reactor. An isotope of cobalt is used in the treatment of cancer. For treating goiter, an isotope of iodine is used. In some cases, it is also possible that the atoms of different elements have different atomic numbers, may have the same mass number. Such atoms are called as isobars. For example, argon with atomic number 18 and calcium with atomic number 20. The number of electrons in these atoms are different, but the mass number of both these elements is 40.
The composition of an atom can be represented symbolically as ZXA, as shown here. The symbol X represents the symbol of the element. The superscript A on the left-hand side of X represents the atomic mass number, and the subscript Z on the left-hand side represents the atomic number of the element. As you have learnt before, atomic number Z gives the total number of protons present in an atom, while the atomic mass number gives the total number of protons and neutrons present in that atom. Let us work on a simple problem before proceeding further. An atom has 29 electrons and 35 neutrons. Calculate the number of protons and the mass number of the element. Also write the complete symbol for the atom. Since atomic number Z is equal to number of protons, which is also equal to the number of electrons in the atom, we can say that the number of protons is 29. We know that mass number A is equal to the sum of the numbers of protons and neutrons. Hence, the mass number of the given element is equal to 29 plus 35, which is equal to 64. Since the atomic number of the element is 29, the atom is copper. The complete symbol for the atom may be represented as shown here. In some cases, atoms of the same element may have the same number of protons, that is, the atomic number, but may have different numbers of neutrons. In other words, the atoms have the same atomic number but different mass numbers. Such atoms are called isotopes. Isotopes of the same element occupy the same place in the periodic table because they have the same atomic number. Let us look at a few examples of isotopes. 99.985% of hydrogen atoms contain only a single proton in their nucleus. This isotope of hydrogen is called protium, 1H1. Remaining 0.015% contain two other isotopes, deuterium, which contains one proton and one neutron, and tritium, which contains one proton and two neutrons. You can see that all these three isotopes have the atomic number 1 and mass number 1, 2, and 3 respectively. Carbon has three isotopes with mass numbers 12, 13, and 14 respectively. Similarly, chlorine, atomic number 17, has two isotopes with mass numbers 35 and 37. Isotopes of the elements other than hydrogen do not have special names. They are represented by simply indicating the mass number on the element's symbol. The chemical properties of an element depend on the number of electrons present and their configuration within an atom, and not on the number of neutrons. Hence, as the isotopes have the same number of electrons, they exhibit similar chemical properties. However, as the mass of isotopes differ due to the different numbers of neutrons present in an atom, their physical properties differ from each other. Some atoms of different elements are found to have the same mass number but different atomic numbers. For example, 18Ar40, 19K40, and 20Ca40 have same mass numbers but different atomic numbers. Such atoms of different elements having different atomic numbers but the same mass numbers are called isobars. Isobars have different chemical properties because they have different atomic numbers. Our atmosphere is made up of many gases. But there are 6 gases, namely helium, neon, argon, krypton, xenon, and radon, which are rare, and collectively they make up about 1% of the atmosphere. These gases do not bond with other elements and hence are called noble gases. Incidentally, these gases are placed in group 18 of the periodic table. Did you know that group 18 is also called a zero group as the valency of the noble gases is 0? In other words, noble gases have a stable electronic configuration as their valence shell is complete. For example, helium has 2 electrons in its outermost shell. This arrangement is known as duplay. On the other hand, neon and other noble gases have 8 electrons in their outermost shell. This arrangement is known as octet. It is because of this duplet and octet arrangement that the noble gases are unreactive in nature. Atoms of other elements, on the other hand, do not have a stable electronic configuration. These atoms therefore attain stability by either having 2 electrons in its outermost shell, like that of helium as per the duplet rule, or by having 8 electrons in its outermost shell, like that of other noble gases, according to the octet rule. Since helium has only 2 electrons in its valence shell, it cannot have an octet. Hence, though it is considered for duplet rule, it is excluded for the consideration of octet rule. In fact, atoms attain this stable electronic configuration by either transferring electrons from one atom to another or by sharing electrons between 2 atoms. When one or more electrons are transferred, the atom formed may be positively or negatively charged. These atoms are called ions. For example, in case of common salt or sodium chloride, chlorine attains the electronic configuration of its nearest noble gas, argon, by gaining 1 electron from sodium atom. Similarly, sodium attains the electronic configuration of its nearest noble gas, neon, by losing 1 electron. In this case, the loss of an electron in the sodium atom results in an overall positive charge, while the gain of this electron by the chlorine atom results in an overall negative charge. On the other hand, hydrogen atoms gain stability by sharing electrons to form a hydrogen molecule. In this case, one hydrogen atom shares its electron with another hydrogen atom to attain the electronic configuration of helium. This sharing of 2 unpaired electrons results in the formation of a bond known as a covalent bond. On the other hand, the pair of electrons is called an electron duplet. For instance, helium has an electron duplet, 1s2, and hence it has a doublet structure. On the other hand, the outer electron structure of the other noble gases is s2p6. This structure is called octet or closed structure. Noble gases are not only important because they have stable electronic configuration, but they have several uses. For instance, helium, being lighter than air, it is used to fill meteorological balloons. It is also used to fill airships. Interestingly, mixture of helium and oxygen is filled in scuba tanks worn by deep-sea divers. Moreover, this mixture of helium and oxygen is also used for treating patients with respiratory problems. Another useful noble gas is neon, which produces red light when electricity flows through it, and hence the gas is used in advertisement signboards. Argon, on the other hand, is used in light bulbs. This gas is also used to provide an inert atmosphere while making silicon and germanium crystals for electronics industry. Like argon, krypton is also used in commercial lighting. The gas is used in lamps, which produce high-intensity light that are used along airport runways and lighthouses. Another noble gas is xenon, which is used in photographic flash bulbs. On the other hand, due to the radioactive nature of radon, It is used as seeds in radiotherapy of cancerous cells. Thus, the noble gases are used in various fields, such as medicine, commercial lighting, as well as in meteorology.